Welcome to day 2 of the biology unit. Today we're going to be focusing on some specific neurotransmitters that you need to know their function within the brain and the body. And we'll get into that today. Now, again, this is a little bit oversimplified. With almost anything that we do, there's going to be a multitude of neurotransmitters that are involved with it. But nevertheless, it gives you a gist that some neurotransmitters are associated with some specific behaviors. So we'll start off with the neurotransmitter acetylcholine. Acetylcholine has a couple of different functions within the body. Within the brain, it's focusing on, it seems to be involved in learning and memory. And it seems to be involved in this memory consolidation process, the process of helping to transfer new memories into more long-term memories. And there's been some research on rats, for example, in which if you block the production of acetylcholine after they have learned a maze, that new memory of that maze seems to be blocked as well, and they're not able to process that in the long term. So it seems to be involved in learning and memory. A reduction in acetylcholine has been associated with Alzheimer's disease. Again, Alzheimer's disease is a disorder, a brain disease in which at least one of the earliest symptoms and the most well-known symptom most associated with Alzheimer's is this loss of memory. And so it makes sense that there's a loss of production of acetylcholine, although that seems to be more of a symptom than a cause really of Alzheimer's. Throughout the body, acetylcholine is the only neurotransmitter that is involved with voluntary muscle movement in the peripheral nervous system. So in other words, it's a neurotransmitter that interacts with the muscles and helps to coordinate their movements. And some of the spider bites that cause paralysis, or some poisons that are used by some indigenous peoples, affect the absorption of acetylcholine. And one of the ways that they create that paralysis is by blocking the absorption of acetylcholine, therefore making you unable to move your muscles voluntarily. Dopamine is probably one of the more well-known neurotransmitters. It is associated with what we call pleasure or reward centers. These are our drive centers, the basic drives of food, water, sex drive. Those dopamine seem to be associated with that kind of drive center. It's often kind of mispresented though. So let's imagine that we have this piece of chocolate cake here. A lot of times it's presented as if when you eat the chocolate cake, you're going to get this rush or flood of dopamine. But that's not quite what's happening here. What's really going to happen is when you see this chocolate cake, assuming you like chocolate cake, when you see this chocolate cake, that's when your brain is going to start flooding you with dopamine. It is going to start, and that's what's going to create that urge, that desire, that want for that chocolate cake. So that production of dopamine is prior to having what you want. It creates, so instead of a reward center, I like to think of it as a desire center. It creates the drive for whatever it is that you actually desire. And so we'll talk about in a little bit later how this can be hijacked by drugs, by recreational drugs, and can therefore create this sense of urge and need for the drug once you stop the natural production of dopamine by getting addicted to those drugs. It is also involved in the brain. So if acetylcholine was involved in voluntary muscle movement throughout the body, dopamine is also involved in movement, but in the brain. It's going to be involved in the motor cortex and helping to coordinate the muscle movements from the brain's side of things. Serotonin is another one that's usually pretty well known. Serotonin is associated with mood. One of the major theories of depression is that depression is caused by a reduction in or lower than normal levels of serotonin in the brain. A lot of major antidepressants are based on that theory. And the problem with any theory about any mental disorder involving a lack of or oversupply of neurotransmitters, we can't really measure neurotransmitter levels in a live brain. It can only happen at autopsy. And so it's difficult exactly to determine whether there really are lower levels of serotonin and whether it's really causing depression or not. But that's at least one theory that's out there. One thing that we do know with moods is that foods that we eat, for example, high carbohydrate foods, can often be converted into and used to create serotonin, and that could explain why if you are ever stressed out and your mood's not at its best, that you may turn to these high fat, high sugar, high carb diets, because your body's going to use that to ultimately help to create serotonin. It may also be an explanation as to why we enjoy being out in the warm sunlight. Again, the body uses or has a process of being able to convert that type of energy into serotonin as well. It's also involved in the hunger drive. And again, we just talked about how it's related to the drive or the urge for carbohydrates, as that is often used to produce serotonin. Two other neurotransmitters that are less well known that you need to know. In our first video for this unit, we talked about inhibitory versus excitatory neurotransmitters. You need to know two major neurotransmitters involved with that process. GABA, or gamma-aminobutyric acid, is the major inhibitory neurotransmitter. It is the neurotransmitter that is often sent by other neurons that are saying, don't fire, don't fire, don't fire. And then glutamate is the major excitatory neurotransmitter, which is processing the opposite message. An overabundance of glutamate has been linked to both hallucinations and to migraine headaches. And if you think about hallucinations, for example, what are hallucinations? Hallucinations are signals in the brain that are misinterpreted as sensory information. And so, what's going on oftentimes is there's an overabundance of glutamate. There's basically random haphazard signals that are going on in the brain that aren't really supposed to be going on there, and your brain wants to interpret them and have meaning for them, so it often gets interpreted as this sensory input that's not really there. Now, neurotransmitters are going to influence behavior on what we call brain pathways, and what we mean by this is certain brain functions and certain brain pathways are really only influenced by one or two neurotransmitters. So, for example, we talked about that reward center, that pleasure center. That's really the primary neurotransmitter that's going to affect that is dopamine. And there aren't going to be too many other neurotransmitters that are involved in that region. And so the brain does have some specialization with neurotransmitters that is very specific to particular regions. Now, neurons also, we talked about in the first video how neurons communicate, and we talked about it as being, we have that overly simplistic view of just one neuron firing. But in reality, anytime our brain does anything, it's starting to form these neural networks in the brain. And these neural networks are basically networks of neurons that are all firing together while completing the same task. And there's what we call the Hebbian principle, developed by David Hebb. And his argument was that neurons that fire together, that fire at the same time, wire together. So neurons that fire together, wire together. And the idea is that, the example that's given here is, someone who's is a musician. Well, as you first start to learn an instrument, for example, you're going to be not that great at it. You're going to make a lot of mistakes. It's not going to sound all that great. Because the neurons that are firing in coordination to produce that music have very weak signals, and so the coordination is not going to be that great. But as you practice and get better, and practice more and get even better, and then keep practicing until you reach a level of expertise, those neurons are going to fire together more efficiently. They're going to create larger synapses and larger surface areas with more receptor sites. It's going to allow more neurotransmitters to be absorb between each other, and it's going to make that communication more efficient. And so we create these neural networks within our brain based on our own expertise and based on our own experiences. Now, the last topic for today is how drugs impact the brain. And we're going to have a whole separate unit on drugs in our states of consciousness unit and exactly how specific drugs impact the brain. But essentially, a drug is going to either act as what we call an agonist or an antagonist. And there's three images off to the right. And we talked about before with a neurotransmitter being released into the synapse and the receiving neuron has these receptor sites for these neurotransmitters, and it's kind of like a lock and key. That first image on the right-hand side at the top in blue, it shows you what a normal neurotransmitter, kind of that connectedness. It doesn't, it's obviously not going to look like this, but it's just showing you the image of what it means, that it has to fit just right in order for the receiving the receiving neuron to really react to this neurotransmitter. Well, agonist drugs are going to mimic a specific neurotransmitter. And so, for example, cocaine is going to mimic dopamine, and it's going to flood into these synapses where dopamine is normally released, and it's going to flood these receptor sites and they basically overload the body on what it thinks is dopamine. But it's really caused by the cocaine. That's what's going to create the high. You're basically reacting strong. It's like a gross oversupply of dopamine in the body. And as we'll talk about in the states of consciousness unit, your body responds to this basically by shutting off the dopamine production that you naturally have. And now all of a sudden you go from getting the high from initially taking cocaine to now you just simply need it to feel normal because your body is no longer normally producing dopamine. So that's what agonists do. Cocaine is just one example. An antagonist is going to block a neurotransmitter. It's going to prevent it from functioning normally. A lot of our pain medications are antagonists. Advil or Tylenol, for example, are going to act as antagonists. They're going to prevent the neurotransmitters that are being sent from neurons that are processing the feeling of pain in an effort to give you that pain relief. So if you think about what Tylenol and Advil do, let's imagine you have a sprained ankle and you are taking Advil or Tylenol, whatever pain medication you take. It's not like it's doing anything to heal the ankle. At best, it's an anti-inflammatory and may help cut down on swelling that may be causing the pain. But in reality, it's not doing anything to heal what's creating the pain. What it's doing is it's blocking the neurotransmitters that are sending that pain signal to help to dampen it down. Now, pain obviously is an adaptive trait. We want to feel pain when we're hurt. It's very problematic when we don't. But once we've gotten a signal, it's nice to be able to shut it off, and that's what those drugs do. Okay, that sums up our discussion of neurotransmitters today. It's a real simplistic kind of introductory topic. We'll get into neurotransmitters throughout the year. If you have any questions, you can always email me at ghsteacher@gmail.com, or you can ask questions in class.